You know how it is.
Yeah.
You want to wrap your head around something complex, but the idea of slogging through dense reports, it can just feel overwhelming.
Yeah, totally.
That's where we come in. Welcome to the deep dive, your shortcut to getting, well, seriously well informed.
Exactly. We take all that information overload and try to boil it down to the core insights. Think of this as your express route to understanding what really counts.
And today we're plunging into something that, well, it influences so much of modern life, the automotive supply chain.
It really does.
You, our listener, were curious about getting a grip on this sprawling global network, so we've got a comprehensive analysis here, automotive supply chain breakdown.pdf. It covers really everything from sourcing raw materials right through to the end of a vehicle's life.
And this source, it's remarkably thorough. It details the processes, the variations across different types of vehicles, market dynamics, the works.
So our mission today,
Our mission is to pull out the key nuggets, those, surprising details, and maybe create some aha moments that make this whole intricate world a bit clearer for you.
okay, let's dive in. Unpack this thing. When you picture a car, I mean, the first thing you probably don't think about is just how many individual parts go into it.
Oh, absolutely not. But the scale is massive. We're talking anywhere from, say, 15,000 to 30,000 components in a typical vehicle,
15,000.
minimum.
Yeah, up to 30,000. It's staggering. And what's really fascinating now is that it's not just a straightforward sequence anymore.
How do you mean?
Well, the automotive supply chain has evolved. It's less of a simple linear chain and much more like a really complex interconnected supply web
Oh, web. Yeah.
with deep interdependencies. So instead of step A, then step B, then step C, you've got numerous suppliers feeding into different stages, often simultaneously.
Gotcha. So less like a bicycle chain, more like a spider web. What are the main hubs or stages in this web, then? We can break it down into several key stages, broadly speaking. First up is raw material procurement. That's getting everything from steel and aluminum to now lithium and cobalt.
Right.
Then you've got part manufacturing, where all those thousands of individual bits are made.
Mm.
After that, vehicle assembly, putting it all together.
Okay.
Then comes really rigorous quality control and testing. Can't skip that. Followed by distribution and retail, getting the car to the dealer and then to you.
It doesn't stop there, does it?
No, absolutely not. You also have to consider aftermarket and end-user services. That's maintenance, repairs, spare parts. And finally, end-of-life management. What happens when the car's done? Recycling? Disposal? That's a big focus now, especially with EV batteries.
Okay, that makes sense. A whole life cycle view. Now, within that journey, the source talks quite a bit about a tiered supplier structure. What's that all about?
Ah, yes, the tiers. This basically maps out the different levels of companies involved in making all those parts and getting them to the final assembly line.
So levels, like a pyramid.
Sort of. At the very top, you have the original equipment manufacturer, the OEM. That's your Ford, your Toyota, BMW, the big brand names you recognize.
Right, the car companies.
Exactly. Although, interestingly, while we call them manufacturers, their main roles these days are often design, engineering validation, brand marketing, managing this whole complex supplier network, and then, yes, the final assembly.
So they're kind of the conductors of the orchestra.
That's a great way to put it, precisely. Then, directly below them, you have the Tier 1 suppliers.
Tier 1, okay.
These companies have a direct relationship with the OEMs. They supply complex systems or modules straight to the assembly line. Think engines, transmissions, complex electronics like ECUs, safety systems, seating, whole interiors.
Wow, so big chunks of the car.
Yeah, and they're often involved quite early in the vehicle development process, too.
Okay, so OEM at the top, Tier 1 supplying the big systems. What's below Tier 1?
That's where you find Tier 2 suppliers. They supply components, sub-assemblies, or maybe process materials to the Tier 1 companies.
Ah, okay. So they supply the suppliers.
Exactly. A Tier 2 might specialize in things like sensors or wiring harnesses, specific types of fasteners, plastic moldings, metal stampings. You get the idea.
Yeah.
So a Tier 2 might make the individual sensors that a Tier 1 then integrates into a complete safety module for the OEM. And Tier 2s often serve other industries too, not just automotive.
And does it keep going? Is there a Tier 3?
Yes, absolutely. Tier 3 suppliers are generally providing more basic components or process raw materials. Think steel producers, aluminum smelters, chemical companies providing specific plastics or rubbers. They feed into the Tier 2s.
Right down to the basics.
And you could even talk about Tier 4, though it gets a bit blurry down there. Tier 4 would be the initial extraction, like the mining companies pulling the raw ore out of the ground.
Wow. It really is a deep web, isn't it? Does having all these layers of this intricate structure cause any problems?
Oh, definitely. Big challenges, particularly around visibility and managing risk.
Visibility.
Yeah. OEMs usually have a pretty good handle on their Tier 1 suppliers. They work closely together. But visibility below Tier 1 into Tier 2, Tier 3, that gets much, much harder.
So they don't always know what's happening further down the line.
Often no, but disruptions frequently start down there. I mean, the perfect example is the recent semiconductor shortage,
Well,
right?
that was huge.
And those were often issues at Tier 2 or Tier 3 foundries, companies the OEMs didn't have direct relationships with, but the impact on car production was absolutely massive.
So a small hiccup way down in the web can send huge ripples all the way up to the big car brands.
Exactly. That's why managing supply chain risk is becoming so much about looking beyond just your direct Tier 1 suppliers. Sometimes OEMs need to engage directly with lower tiers, especially for critical components or materials.
And the source mentions vertical integration too. Is that like bringing things in-house?
Yes, precisely. Some OEMs are looking at that as a strategy, especially for really critical things like maybe battery cells or software, to gain more control and reduce that risk.
Okay, so this complex tiered web is how it's structured. Now let's dig into what they're actually making at these different levels, starting right at the beginning, raw materials. Where does all that stuff come from?
Well, traditionally, cars are made of a lot of steel. It's strong, relatively cheap. Then there's aluminum, which is key for making cars lighter, improving efficiency. Plus, of course, plastics, rubber, glass, sourced from all over the world.
Standard stuff.
Ugh,
But EVs have changed the game, haven't they?
massively. EVs need a whole new shopping list, mainly for the batteries. We're talking lithium, cobalt, nickel, manganese, graphite, and then rare earth elements for the electric motors.
Yeah, I've heard sourcing those can be tricky.
It's a major challenge. Demand is just skyrocketing as EV production ramps up, and the supply chains for many of these minerals are geographically concentrated.
Concentrated where?
Well, the mining might be in a few places, but the processing is often heavily dominated by China, especially for things like lithium, cobalt, and graphite.
Ah, so that creates geopolitical risks.
Absolutely. Trade tensions, supply disruptions, it's a big vulnerability. Plus, there are environmental and human rights concerns associated with mining some of these materials, not to mention significant price volatility. A sudden spike in cobalt prices can directly impact the cost of an EV battery.
So sourcing is complex, whether it's old school steel or new school lithium. What happens once those raw materials are secured? How do they become car parts?
Okay, so Tier 3 suppliers take those raw materials and transform them, maybe making steel sheets or aluminum ingots. Then Tier 2 suppliers use those processed materials to manufacture more specialized parts and subassemblies.
And the source mentions some specific manufacturing processes.
Yes, it highlights quite a few key ones used at these Tier 2 and 3 levels. There's casting, pouring molten metal into molds, sand casting for complex shapes like engine blocks, die casting for high-volume, precise parts.
Okay.
There's forging, using immense pressure to shape metal, which creates really strong components like crankshafts. Stamping or pressing is used for shaping sheet metal into body panels, doors, hoods, fenders.
Right, like the big presses you mentioned.
Exactly. Then extrusion for parts with a constant shape, like aluminum trim pieces. Injection molding is huge for creating intricate plastic parts, dashboards, bumpers, interior trim. And finally, machining, using cutting tools for ultimate precision on engine components and things like that.
There's a lot of different ways to shape metal and plastic.
It is. And it shows the specialized skills needed down in Tiers 2 and 3. Even small efficiency gains in these processes can save the OEMs a lot of money down the line.
So Tier 2 and 3 make all these individual bits and pieces using these processes. Then Tier 1 comes in.
Exactly. Tier 1 suppliers are the integrators. They take all those components from Tier 2 and Tier 3 and assemble them into the major systems or modules that get delivered directly to the OEM's assembly line.
Like the engine or the whole dashboard.
Precisely. Complete powertrain systems, chassis components, entire interior modules, complex electronics, safety systems. They put it all together. And often this delivery is timed perfectly using just-in-time or just-in-sequence methods, so the parts arrive exactly when needed on the assembly line.
The source also talked about modularity being a trend. What's the advantage there?
Yeah, modularity means Tier 1s are delivering even bigger, pre-assembled, often pre-tested chunks to the OEM. Think of the entire front-end assembly of the car or the complete cockpit module.
Ah, so the OEM is putting together fewer, bigger pieces.
Essentially, yes. It simplifies the final assembly process at the OEM plant, speeds things up, and can potentially improve quality since the module is built and tested by the specialized Tier 1.
Makes sense. Fewer connections to make on the final line. Now, with this huge web of suppliers, OEMs, Tier 1s, 2s, 3s, how do the car companies manage it all, keep it running smoothly?
That's where supplier relationship management, or SRM, is absolutely critical. It's not just about placing orders, it's actively managing the relationship.
What does that involve?
Well, it includes things like continuously evaluating supplier performance, quality, delivery, cost. Negotiating contracts, obviously. Managing risks, like making sure you're not overly reliant on a single supplier for a critical part.
Diversification.
Exactly. Fostering collaboration and transparency, integrating technology for better communication and data sharing, maybe encouraging local sourcing to shorten lead times. It's multifaceted.
It sounds like a constant juggling act.
It really is. And it's evolving fast, especially with EVs and all the advanced electronics. OEMs are finding they need to engage more directly with suppliers further down the chain, Tier 2 or even Tier 3, for things like battery cells or semiconductors.
Bypassing Tier 1 sometimes.
In some cases, yes. They need that direct line to secure the supply, maybe influence the technology roadmap, and just get better visibility into potential issues with these absolutely vital components. They can't afford another chip crisis.
Understood. Okay, so we've got the structure. The parts are being made and managed. Now let's get to the really cool part. How does that pile of components actually become a shiny new car? Talk us through vehicle assembly.
Right. This is where it all comes together at the OEM's final assembly plant. It's like a highly choreographed ballet of robots and people. The source breaks it down into core stages.
Stage 1.
It usually starts with stamping in the press shop. Giant rolls of sheet metal are fed into massive presses. The source mentions Toyota using 1,600-ton presses, which stamp out the body panels, doors, roof, hood, fenders.
1,600 tons. That's incredible force. What happens after the panels are formed?
They move to the body shop. Here, hundreds, sometimes thousands, of robots join these panels together to create the vehicle's basic skeleton, what's called the body in white, or BIW.
How do they join them? Welding.
Mostly, yes. Robotic spot welding has been the standard. But now, especially with lighter materials like aluminum or mixed materials, and for EV structures, we're seeing more laser welding, structural adhesives, and even rivets being used alongside welding.
Okay, so now we have a bare metal body shell. Next is the paint, right? The pretty part.
Exactly. The BIW goes through the paint shop. This is a super clean, multi-step process crucial for both looks and corrosion protection. It involves cleaning, pre-treatment, an electrocoating or e-coat dip for corrosion resistance, sealants applied to joints, then layers of primer, the color base coat, and finally the protective clear coat.
And lots of baking in between.
Oh yeah, big ovens bake and cure the paint layers. It's a long and energy-intensive process.
Okay, painted body. What's next? Putting in the guts.
That's a good way to put it. Next is powertrain installation. This is often called engine dress, or sometimes the marriage, where the powertrain is joined to the body.
And that differs for EVs versus gasoline cars.
Significantly. For a traditional car, it's installing the engine, transmission, exhaust system. For an EV, it's the electric motor, power electronics, and the really big, heavy battery pack. The source notes EV batteries often come up from underneath the car, requiring specialized lifting equipment and lots of safety protocols due to the high voltage.
Right. Then it must really start looking like a car.
It does. The next major stage is final assembly, sometimes called trim and chassis. This is where pretty much everything else goes in.
Like the interior?
Yep, dashboard seats, carpets, headliner, and exterior parts like bumpers, lights, grille, windows, plus all the wiring harnesses, fluid fills, brake fluid, coolant, windshield washer, suspension components, brakes, and finally, the wheels and tires.
I heard they sometimes take the doors off.
That's right. Often the doors are removed after the paint shop to allow better access for installing the interior components, and then they're reattached later in the final assembly stage.
Clever. So after all that, then you just drive it off the line.
Almost. Quality control and testing is happening throughout the whole process, but there's a big focus at the end. Vehicles go through system checks, maybe a water leak test booth, wheel alignment, brake tests, sometimes a short run on rollers or a test track. There's a final inspection under bright lights for any paint or body defects, and all the electronics and software get programmed and tested.
And the crash test.
Those happen much earlier during the vehicle development phase. Using prototypes, they don't crash test every car coming off the line.
Okay, good to know. It sounds like a massive coordinated effort. How is the shift to EVs changing this whole assembly process?
It's having a huge impact. As we said, the powertrain installation is totally different. While EVs technically have fewer moving parts than the powertrain, handling that massive battery is a major challenge. The weight, the size, the safety requirements.
Right.
Plus, EVs often use more lightweight materials like aluminum, which requires different joining techniques in the body shop, more adhesives, rivets, specialized welding. And the level of software and electronics integration is way higher, meaning more programming and testing at the end of the line.
So converting a plant from making gasoline cars to EVs isn't trivial.
Not at all. It requires significant investment in new tooling, different layouts, retraining the workforce. It's a major transformation. The basic stages might look similar, but the specifics within each stage can be radically different.
That makes sense. And to really dig into those specifics, the source breaks down the supply chains for different types of powertrains. Let's start with EVs, since they're changing so much.
Okay, EVs. As we mentioned, the battery is king here. It dictates a huge part of the supply chain and the vehicle's cost and performance.
And making the battery cells themselves is complex.
Extremely. The source details an 8-step process for battery cell manufacturing, starting with mixing the chemical slurry, coating it onto electrodes, drying, pressing, calendaring, slitting, assembling the cell layers, packaging, filling with electrolyte, sealing, and then a crucial formation, aging, and testing phase. It's very precise, almost like a lab process done at industrial scale.
Wow. And there are different types of batteries, right? Chemistries?
Yes, the source mainly compares the two dominant lithium-ion types, NMC, nickel manganese cobalt, and LFP, lithium iron phosphate.
Pros and cons.
NMC generally offers higher energy density, more range for the same weight, but relies on cobalt and nickel, which have those sourcing challenges we discussed, and can have a lower thermal runaway threshold, meaning potentially a higher fire risk if damaged. LFP uses more abundant and cheaper iron and phosphate, is generally considered safer with a higher thermal threshold, and offers longer cycle life.
But maybe less range.
Historically, yes, LFP had lower energy density. But it's improving rapidly, and many manufacturers, especially in China, are adopting it for standard range vehicles due to cost and safety benefits. It can struggle a bit more in very cold temperatures, though.
Okay, so that's the cell. How does it become a car battery pack?
Right. The cells are just the start. They get assembled into modules. Then these modules are combined into the final pack. Crucially, the pack also includes the battery management system, the BMS.
What does the BMS do?
It's the brain of the battery. It monitors the voltage, current, and temperature of every cell, protects against overcharging or deep discharging, balances the charge between cells to maximize life, and detects faults. It's vital for safety and longevity.
And keeping it cool.
That's the job of the thermal management system, or TMS. Most EV packs use liquid cooling systems, circulating coolant through plates or channels within the pack to keep the cells in their optimal temperature range, typically around 20 to 45 degrees Celsius. Overheating is bad, but so is being too cold.
Got it. BMS and TMS. What else goes into the pack?
Structural components to protect the cells, high voltage electrical connections, safety disconnects. It's a complex piece of engineering in itself.
And beyond the battery, EVs also need motors and electronics.
Correct. Electric motor production involves winding copper coils for the stator and assembling the rotor. The source mentions different motor types, like permanent magnet synchronous motors, PMSM, which often use rare earth magnets, versus induction motors or switched reluctance motors. Then you have the power electronics.
Like,
Key components here are the traction inverter, which converts the battery's DC power to AC power for the motor and handles regenerative braking. The DC-DC converter, stepping down the high battery voltage for the car's regular 12-volt systems. Lights, wipers, infotainment. The onboard charger, OBC, that converts AC from the grid to DC to charge the battery. And the vehicle control unit, VCU, which coordinates everything motor, battery, charger, driver inputs.
lots of complex electronics. And the sourcing challenges for EVs. We touched on minerals.
Yeah, it really boils down to those critical minerals for batteries and motors.
Yeah.
The geographical concentration, the geopolitical risks, the massive investment needed to scale up mining and processing, the price volatility, and the ethical and environmental concerns surrounding extraction. It's the biggest headache for the EV supply chain right now.
And how are car makers trying to cope?
The source mentions several strategies. forming partnerships or joint ventures directly with mining or chemical companies, diversifying sources away from single regions, investing heavily in domestic battery production plants, like all the gigafactories popping up, developing battery recycling capabilities, researching alternative battery chemistries that use fewer critical minerals, and even vertical integration, bringing cell production in-house.
Makes sense. A multi-pronged approach.
Yeah.
Now, shifting gears completely, what about those huge diesel semi-trucks? Their supply chain must be focused on different things.
Absolutely. For heavy-duty trucks, it's all about durability, massive power and torque, fuel efficiency under heavy loads, and meeting incredibly strict emissions regulations.
So the engines are built differently.
Very much so. Heavy-duty diesel engine manufacturing involve casting massive engine blocks, often from iron alloys for strength, precision machining of things like cylinder bores, which often use replaceable wet liners so the engine can be rebuilt more easily, and assembling very robust components. Think high-pressure, common rail fuel injection systems and sophisticated turbochargers, often with variable geometry, VGT, for better performance and efficiency. They're built to last hundreds of thousands, even millions of miles, with proper maintenance and overhauls.
And the frame of the truck itself.
That's crucial too. The source details the production of the chassis frame rails, typically a ladder frame design made from high-strength steel, HSLA, or heat-treated alloys. These are formed using processes like roll forming or press braking, then precisely cut, drilled, and joined together, usually with heavy-duty bolts, sometimes welding, and they need serious protective coatings against corrosion.
And you mentioned emissions are a big deal for trucks.
Huge. Meeting modern diesel emission standards adds enormous complexity to the supply chain. The source details the key systems: exhaust gas recirculation, EGR, to reduce NOx formation, a diesel oxidation catalyst, DOC, a diesel particulate filter, DPF, to trap soot, which requires periodic regeneration cycles to burn off the soot and eventually needs ash cleaning and selective catalytic reduction, SCR.
That's the one that uses DA fluid.
Exactly. SCR injects diesel exhaust fluid, DEF, which is basically urea solution, into the exhaust stream. It reacts in the SCR catalyst to convert harmful nitrogen oxides, NSOx, into harmless nitrogen and water. There might also be an ammonia slip catalyst, ASC, afterward.
Wow, that sounds like a whole chemical plant bolted onto the truck.
It practically is. Manufacturing, integrating, and controlling all these emissions components, catalysts, filters, injectors, sensors, control units, is a massive part of the heavy-duty truck supply chain. And these systems can sometimes be sources of maintenance issues, too.
And assembly must be different, too, right? Trucks are often customized.
Very true. The final assembly involves marrying the massive chassis, powertrain, and cab, integrating all the systems, but then there's often significant customization or upfitting, depending on the truck's purpose, attaching a specific type of trailer body, a dump mechanism, a crane, whatever. This requires flexibility in the assembly process and skilled labor.
So, a supply chain defined by robustness and complex emissions tech. How does that compare to your typical gasoline sedan or pickup truck?
Well, the gasoline vehicle supply chain is obviously very mature, but it's still constantly evolving to improve fuel economy and reduce emissions further.
What are the key manufacturing aspects there?
The source dives into engine block and head manufacturing. There's been a big shift from heavier cast iron towards lighter aluminum alloys. It discusses various casting methods, sand casting, but also high-pressure die casting, HPDC,
Yeah.
and low-pressure die casting, LPDC, for aluminum parts, followed by extensive CNC machining for precision. Milling surfaces, drilling and tapping holes, boring and honing cylinders, line boring for crankshaft bearings, Solvis grinding. It's incredibly precise work.
And fuel injection, that's changed a lot too, hasn't it?
Definitely. The source compares traditional port fuel injection, PFI, where fuel is sprayed into the intake port just before the valve, with gasoline direct injection, GDI, where fuel is injected at much higher pressure directly into the combustion chamber.
GDI is better for efficiency and power, right?
Generally, yes, but it can have downsides like potential issues with carbon buildup on intake valves, since fuel isn't washing over them, and sometimes higher particulate matter emissions. That's why we're now seeing dual injection systems on some engines using both PFI and GDI to get the benefits of both. Manufacturing these high-pressure pumps and injectors requires extreme precision.
And for emissions on gasoline cars, it's mainly the catalytic converter.
Primarily, yes. The three-way catalytic converter is the workhorse. The source explains its construction. A ceramic or metal honeycomb substrate coated with a wash coat to increase surface area and then infused with tiny amounts of precious metals, typically platinum, PT and palladium PD to oxidize carbon monoxide and hydrocarbons, and rhodium RAH to reduce nitrogen oxides.
All happening at once.
Ideally, yes, when the engine is running close to the perfect air-fuel ratio, stoichiometric. This requires sophisticated engine management using oxygen sensors before and after the converter to constantly adjust the mixture. And the reliance on those precious metals makes converters expensive and a target for theft, unfortunately.
So even for established gasoline tech, there's constant innovation driving supply chain complexity. Now, what about hybrids? They seem like they'd be the most complicated, mixing both worlds.
They definitely introduce their own set of challenges, bridging that gap between ICE and EV. The source highlights the powertrain integration complexity, just physically packaging both an engine and electric motors, plus a battery and power electronics, is tough.
And controlling it all.
That's the other big challenge. The control system software has to be incredibly sophisticated to seamlessly blend power from the engine and motor, manage regenerative braking, and optimize for efficiency under all driving conditions. Plus, ensuring reliability with more components and complex software is key.
Who are the big players in hybrids?
Toyota is famous for its power split hybrid system, which they've used in the Prius and many other models. Honda and Ford also have significant hybrid offerings, and demand for hybrids has been really strong lately, sometimes straining the supply chain for specific hybrid components like transmissions or power electronics.
You mentioned Toyota's power split system. Are there other types?
Yes, the source outlines the main categories. Power split uses a planetary gear set to link the engine, motor generator 1 and motor generator 2, allowing power to flow through mechanical and electrical paths simultaneously. Parallel hybrids have both the engine and electric motor capable of directly driving the wheels, often via a conventional transmission. These can range from mild hybrids with small motors to full hybrids. And series hybrids, less common in cars, use the engine purely as a generator to charge the battery, with only the electric motor driving the wheels.
So different engineering approaches. What about hybrid batteries? Are they like EV batteries?
Similar, but often different in size and sometimes chemistry. Many traditional full hybrids, like the Prius, historically use nickel metal hydride, NiMH, batteries. They're known for good cost, safety, and tolerance to temperature swings, even if their energy density isn't as high as lithium-ion.
But lithium-ion is used too.
Increasingly, yes, especially in plug-in hybrids, PHEVs, which need a larger battery for decent electric-only range, and also in many newer full hybrids and mild hybrids where space and weight are tighter. The battery management system, BMS, is just as critical in a hybrid as in an EV to manage the battery's health and performance.
And the brain coordinating the engine and motor.
That's usually called the Hybrid Control Unit, HCU, or sometimes integrated into the overall Vehicle Control Unit, VCU. It's constantly making decisions based on driver input, speed, battery charge, etc., to decide when to run on electric power, when to use the engine, when to use both, and when to recharge the battery. It's incredibly complex software.
So the hybrid supply chain is really about managing two different sets of components.
Essentially, yes. Sourcing traditional engine and transmission parts, plus batteries, motors, and power electronics. The integration challenge, both physical and software, is huge. And logistics can be complex too, managing the flow of both types of parts. Plus, fluctuating demand between hybrids, EVs, and ICE vehicles adds another layer of planning difficulty for suppliers and OEMs.
Okay, wow. So no matter the powertrain, building the vehicle is incredibly complex. Now, the cars are built. How do they actually get from the factory gates to the dealerships, potentially halfway across the world? Let's talk global logistics.
Right. Once that car rolls off the line, its journey is far from over. Automotive logistics is a massive global industry in itself. It covers everything from inbound logistics, getting all those thousands of components to the assembly plants, often using those just-in-time or just-in-sequence methods we mentioned.
Right, parts arriving just as they're needed.
Exactly. Then there's outbound logistics, also called finished vehicle logistics, or FVL. That's moving the completed cars from the factory to the dealers. And also aftermarket logistics, distributing spare parts for repairs and maintenance. It's a vast network.
What are the main ways they move the finished cars? I picture those big ships.
Ocean shipping is definitely key for international transport. The most common method is using specialized roll-on, roll-off vessels, RoRo ships. They're essentially giant floating parking garages designed for vehicles to be driven directly on and off.
Fast loading, I guess.
Very efficient loading and unloading, yes. But the vehicles are somewhat exposed during transit, An alternative mentioned in the source is container shipping using standard containers fitted with special racking systems, sometimes called cars in containers or CIC. This offers better protection and more flexibility in shipping routes, but it involves more handling.
And on land,
Yeah.
trucks and trains.
Absolutely. Road transport using car carrier trucks, those open or sometimes enclosed trailers you see on the highway, is essential, especially for the final delivery leg to dealerships. Rail transport using specialized multi-level rail cars called autoracks is very common for moving large volumes of vehicles over long land distances, like across North America.
Any other ways?
Air freight is occasionally used, but it's very expensive, so usually only for extremely high-value vehicles or urgent emergency shipments. And bulk shipping is used for raw materials on the inbound side.
You hear a lot about port congestion being a problem. How does that fit in?
Ports are absolutely critical choke points. They, along with associated vehicle processing centers, VPCs, handle the loading, unloading, temporary storage, customs clearance, and inspections. VPCs often perform value-added services too.
Like what?
Things like the final pre-delivery inspection, PDI, installing accessories, port processing options, or PPO, washing the vehicles, maybe performing software updates, or even battery charging and maintenance for EVs that have been in transit for a while.
And congestion really jams things up.
Hugely. Recent years have seen major bottlenecks at ports worldwide due to surges in demand, labor shortages, infrastructure limitations, and other disruptions. When ports get clogged, vehicles can sit for weeks, causing massive delays and adding costs throughout the chain.
So, tracing the journey of a finished car, what are the typical steps to get it to the dealer lot?
Okay, the FEL process usually goes something like this. Vehicle exits the factory gate. Initial transport, probably by truck or rail, to a domestic distribution hub or an export port.
Okay.
If it's being exported, there's port handling, storage, processing, loading onto a ro-ro or container ship, then the ocean transit itself. On arrival at the destination country, import port handling, unloading, customs, maybe moving to a VPC.
Then the VPC does its thing.
Right, inspections, any necessary prep work or accessory installation. Then the final distribution leg, usually by truck, sometimes rail, to the specific dealership. And finally, arrival at the dealer's lot.
Oh, a lot of steps and handoffs.
It is. It requires incredibly tight coordination between the OEM, specialized logistics providers, shipping lines, port authorities, trucking companies, rail operators. They rely heavily on transportation management systems, TMS, and VIN tracking to keep tabs on every vehicle. Collaboration is key.
And you mentioned EVs earlier. Are there special rules for shipping them, especially the batteries?
Yes, this is a huge factor now. Lithium-ion batteries, especially large automotive ones, are classified internationally as Class 9 dangerous goods or hazardous materials.
Why is that? Fire risk.
Exactly. The main concern is thermal runaway, a chain reaction where a damaged or faulty cell overheats, potentially causing a fire that can spread rapidly. So transport is heavily regulated.
What kind of regulations?
There's a fundamental requirement called UN 38.3 testing. All lithium battery designs have to pass a rigorous set of tests simulating transport conditions, vibration, shock, heat, short circuit, etc. Manufacturers also need to provide a test summary document. Then there are specific rules depending on the mode of transport.
Like air versus sea.
Precisely. Air transport, governed by IATA rules, is the strictest. Large standalone batteries are often restricted to cargo aircraft only. There are limits on the battery's state of charge, usually 30% SOC or less, and very specific packaging and labeling are required. Shipping damaged, defective, or recalled DDR batteries by air is often forbidden entirely.
And sea or road.
Sea transport, IMDG code, is generally less restrictive than air, but still demands robust packaging. Road and rail rules, like ADR in Europe or DOT HMR in the US, also require UN 38.3 compliance, proper packaging, labeling, and sometimes have specific routing or handling requirements. There are often stricter rules for shipping those DDR batteries too, requiring specialized fire-resistant containers.
So the battery adds a whole layer of complexity and cost to shipping EVs.
A massive layer. The sheer size and weight of EV packs, combined with these dangerous goods regulations, make logistics significantly more complex and expensive compared to shipping a regular gasoline car. It's even led to discussions about potentially shipping high-voltage batteries separately from the vehicles in some cases, though that adds its own logistical hurdles.
It sounds like the whole FEL sector is under a lot of pressure then.
Definitely.
Yeah.
Capacity constraints, not enough ships, trucks, or rail cars sometimes, the port congestion issues, and now the added complexity and cost of handling EVs and their batteries. It's forcing innovation, like exploring that CIC container shipping more, and a huge push towards better technology for tracking, visibility, and collaboration across the entire logistics network.
Okay, so after navigating that complex journey, the cars finally arrive at the dealerships. What happens on ground there? What's the dealership's role?
Well, the dealership is that crucial final link, the main interface with us, the consumers. They handle the sales process, manage the inventory of new and used cars, and usually provide service and maintenance too.
And it's mostly a franchise model, right?
Yeah.
Independent businesses selling a specific brand.
Traditionally, yes. The franchise model dominates, where dealers are independent but operate under strict agreements with the OEM. However, we're seeing some disruption here. Tesla famously uses a direct-to-consumer (DTC) sales model without franchise dealers. And some established OEMs are experimenting with an agency model, especially in Europe.
Agency model, what's that?
In the agency model, the OEM actually retains ownership of the vehicle inventory and sets the final non-negotiable price. The dealer acts more like an agent, facilitating the sale, handling test drives and delivery, and earning a fixed fee per vehicle sold rather than profiting from the margin between invoice and selling price.
Interesting. So less haggling.
Potentially, yes. It's still evolving. But back to the traditional model, how do dealers actually get the new cars they sell? Do they just phone up Ford or Toyota and order 50 sedans? If only it were that simple. No, the source explains the OEM allocation process. It's how the manufacturers decide which specific vehicles go to which specific dealers. It's not really an order system in the traditional retail sense.
So how do they decide?
It's usually based on a complex formula that weighs several factors. A dealer's past sales performance is often huge, how many cars they sold previously, especially of similar models. How quickly their inventory turns over, known as turn rate, is also critical. Faster selling dealers generally get more cars.
Makes sense. Sell more, get more. What else?
Their current inventory level, often measured in days supply, market demand in their specific geographic area for particular models, the dealer's overall performance against various OEM metrics like customer satisfaction scores, sales efficiency, how well they sell what they're allocated, and of course, the simple availability of specific models and configurations from the factory.
Sounds complicated. And maybe not always transparent for the dealers.
Dealers definitely find it opaque sometimes. The exact weighting of factors isn't always clear. OEMs might hold back some desirable models for reserve allocations. Dealers might need to hit certain inventory thresholds. The timing of when allocated vehicles actually arrive can be unpredictable. It can lead to disputes.
So what can dealers do to try and get the cars they want or need?
Well, the obvious one is sell aggressively to keep that turn rate high. Sometimes they might strategically accept less popular models from the OEM to potentially get better access to the hot sellers. Using their inventorial management systems, IMS, effectively to forecast and demonstrate need can help. And engaging in dealer trades, swapping vehicles with other dealers, is very common to get a specific car a customer wants that wasn't allocated to them.
Okay, so allocation is complex. Once they have the cars, how do they manage that inventory on the lot?
Yeah.
What are the strategies?
The source covers the two main production strategies that influence dealer inventory: build-to-stock, BTS, and build-to-order, BTO.
BTS is the traditional way.
Mostly yes, especially in North America. OEMs forecast demand and build cars to stock, shipping them to dealers who then hold them in inventory, ready for immediate sale. The big advantage is immediate delivery for the customer. It also allows for economies of scale in manufacturing.
Downsides.
High holding costs for the dealer, financing the inventory, insurance, lot space. The risk of getting stuck with unpopular models or configurations if the forecast was wrong, potential for oversupply leading to discounting.
And build to order, BTO.
That's where production only starts after a specific customer order is placed. It's much more common in Europe for many luxury brands, and of course Tesla operates largely this way.
Advantages there.
Much lower inventory holding costs and risk for the dealer and OEM. Customers get exactly the configuration they want, less waste.
But you have to wait, right?
Exactly. Longer wait times for the customer is the main drawback. It also requires very flexible manufacturing and tight supply chain coordination. The cost per unit might even be slightly higher due to less scale efficiency compared to mass BTS production.
Do they mix these strategies?
Oh yeah, many use a hybrid approach. They might build popular configurations to stock, but allow orders for less common ones. And even within BTS, dealers have flexibility through things like reconfiguring options or those dealer trades. Tesla's BTO success is often linked to their vertical integration and strong IT systems managing the whole process.
How do dealers keep track of it all? The cars, the costs.
They rely heavily on inventory management systems, specialized software. They track key performance indicators or KPIs like the overall days supply for the dealership, the inventory turnover rate, how long specific cars have been sitting, days in stock, and sometimes sophisticated metrics like profit per day for each unit.
And getting cars beyond allocation.
Right. Sourcing involves more than just new cars from the OEM. Trade-ins are huge for used inventory. They also buy cars at auctions, sometimes directly from consumers, and do those dealer trades. Pricing and merchandising are key, using market data, running promotions on older stock, having a strong online presence, managing their floor plan, financing the loans they use to buy inventory and its interest costs is critical, and just meticulous record keeping.
I've always wondered where the real profit comes from for a dealership. Is it all selling new cars?
Actually, no. New car sales generate the most revenue, but the profit margins are often quite thin. Profitability there depends heavily on hitting volume bonuses from the OEM, getting manufacturer incentives, and something called holdback.
Holdback.
It's a small percentage of the car's invoice price that the manufacturer pays back to the dealer later. It helps ensure the dealer makes at least some profit, even if they sell the car close to invoice price.
So where do they make better margins?
Used cars. While the revenue per used car is lower than new, the gross profit margin is typically much higher. Used cars are a major profit center.
Okay. What else?
Fixed operations, that's the service department and the parts department. These consistently generate the highest percentage of gross profit for most dealerships. Regular maintenance, repairs, it's steady business.
The service pays.
Exactly. And don't forget the F&I office, finance and insurance, selling car loans, extended warranties, GAP insurance, paint protection. That's another very significant driver of overall dealership profitability.
Right, and trade-ins seem crucial for feeding that used car operation.
Absolutely vital. Trade-ins are the #1 source of used inventory for most franchise dealers. It makes buying a new car convenient for the customer and gives the dealer a vehicle they can inspect, recondition in their service department, more profit, and then resell. The appraisal process is key. They need good market data to offer a fair price but still leave room for profit. They face a lot of competition now from online buyers and used car giants for those trade-ins, though.
So dealership success is really about balancing a lot of spinning plates. OEM rules, market demand, managing inventory, sales tactics, and those profitable back-end operations.
Precisely. It's a complex balancing act.
Okay, we followed the car's journey, but the market itself isn't uniform. The source discusses market segmentation, luxury brands versus mid-range or budget brands. How different are their supply chains?
They're fundamentally different, really, because their core values and target customers are different. Luxury brands think Mercedes, BMW, Lexus focus on exclusivity, prestige, premium materials, advanced tech, and justify a high price.
Right.
Mid-range or budget brands, Toyota, Honda, Ford, Hyundai, emphasize reliability, practicality, value, affordability. And then you have premium brands like Acura or Infiniti, or even high-end trims of mainstream brands that try to bridge that gap. These priorities shape everything from material sourcing to manufacturing to the dealership experience.
How does that show up in manufacturing and materials?
Luxury cars typically use higher grade materials. You can see and feel real wood, metal trim, top quality leather, soft touch plastics everywhere. Their manufacturing often involves more hands-on finishing, tighter tolerances for panel gaps, and more effort spent on refinement, quietness, ride comfort. They pour R&D into driving dynamics and the latest, sometimes unproven, tech.
And budget brands.
They prioritize cost effectiveness, so durable cloth seats, harder plastics, and less visible areas. Manufacturing is often highly automated for efficiency. Engineering focuses on proven reliability, good fuel economy, meeting safety standards affordably. It's about delivering dependable transportation at a competitive price.
Does that difference extend down to the component level? Sourcing parts.
Definitely. Luxury OEMs usually have much stricter specifications for their suppliers. They demand premium materials, require more extensive validation testing, and have less tolerance for variations. This means components often cost more.
And repairs might cost more, too.
Often, yes, because the parts themselves are more expensive or specialized. Budget brands prioritize reliability and durability at cost. often using more standardized components sourced from suppliers competing aggressively on price. This generally leads to lower parts and repair costs down the road.
What about how they handle the cars, logistics, dealerships?
Luxury brands often get preferential treatment in logistics, maybe more use of enclosed carriers to protect the paint, more meticulous handling at ports and BPCs, and the dealership experience is night and day.
How so?
Luxury dealerships are designed to be upscale showrooms. Staff are highly trained, often providing a personalized concierge-style service. They offer premium amenities, fancy waiting areas, loaner vehicles, maybe pickup and delivery for service. It's all about reinforcing the brand's exclusivity and building a long-term relationship. Budget dealerships are typically more functional, focused on efficient sales volume and service throughput. Clean and professional, but less opulent.
So how do these fundamentally different approaches affect their overall supply chain strategy?
Luxury brands, with their focus on customization and higher profit margins per vehicle, might lean more towards build-to-order or hybrid strategies. This allows for personalization and reduces the risk of holding expensive inventory. Their supply chain complexity comes from managing customization, integrating cutting-edge tech quickly, and sourcing specialized, lower-volume parts.
And budget brands.
They generally rely more on build-to-stock to ensure vehicles are readily available at affordable prices. Their lower margins mean they depend on high sales volume. So their supply chain complexity lies in managing vast global networks, producing huge volumes efficiently, and relentlessly driving down costs at every step. The premium segment tries to find a balance somewhere in between.
So the entire chain, from mine to showroom, is tailored to that end customer and brand promise.
Exactly. It's a completely different philosophy baked into the entire operation.
Okay, one last piece of this huge puzzle the source covers is the automotive auction ecosystem. Where do auctions fit into the supply chain picture?
Auctions play a really vital role, primarily as a marketplace, providing liquidity for used vehicles, but also for off-lease vehicles, retired rental or corporate fleet vehicles, repossessed vehicles, and even salvage or damaged vehicles from insurance companies.
So it's mainly for cars that have already been owned.
Predominantly, yes. They're a primary channel for sellers like OEM finance arms, selling off lease returns, rental companies rotating their fleets, banks, insurance companies, dealerships wanting to wholesale unwanted trade-ins or aged inventory, and even government agencies selling surplus vehicles.
And who buys at these auctions? Mostly dealers.
Dealers are the biggest buyers, using auctions as a major source to acquire the used inventory they need for their lots, supplementing the trade-ins they get.
There's a big wholesale market connecting sellers and buyers of used cars.
Exactly. And critically, the competitive bidding process at these large auctions helps establish wholesale market values for used vehicles. It's a key mechanism for price discovery, which then influences the retail prices you see on dealer lots and in pricing guides. Auctions help keep the whole used car market flowing efficiently.
What are the different kinds of auctions out there?
There's a variety. You still have traditional physical auctions where dealers go in person, walk the lanes, inspect cars, and bid live. But online auctions have exploded in importance. Many now offer simulcast bidding, where online participants bid in real time against the people physically present. There are also timed online-only auctions.
And different companies specialize.
Yes, major players like Manheim and Odessa focus heavily on dealer-only wholesale auctions. Companies like Copart and IAA, Insurance Auto Auctions, specialize in salvage and damaged vehicles, often selling to rebuilders or dismantlers. Then you have newer online platforms like ACV Auctions, facilitating dealer-to-dealer sales with detailed digital condition reports. And of course, collector car auctions like Barrett-Jackson or Mecum, and government auction sites like GSA Auctions.
You mentioned dealer only. Can anyone go to these auctions?
And not usually the big wholesale ones. Access is typically restricted to licensed dealers who register with the auction company, often using a service like Auction Access for verification. Salvage auctions might have different rules, sometimes allowing public access depending on local regulations. Collector and government auctions are often open to the public.
How does the process work for a dealer buying at auction?
First, they register. Then they do their homework researching vehicles coming up for sale, reviewing condition reports, checking vehicle history, Carfax, AutoCheck, looking at photos online, or inspecting cars in person if it's a physical sale. Then comes the bidding, which can be fast-paced. If they win a vehicle, they handle the post-sale process. Payment, auction fees, taxes. They might arrange a post-sale inspection, PSI, for reassurance. Finally, they sort out the title transfer and arrange transportation to get the car back to their dealership.
Do the auctions offer other services?
Yes, lots. They often provide detailing, minor reconditioning, marshaling and storage, title processing help, arbitration services if there's a dispute about the vehicle's condition, and even floor plan financing options to help dealers fund their auction purchases.
What about unsold new cars? Do they ever end up at auction?
It's less common, but the source notes it can happen occasionally, perhaps for aged inventory or models the manufacturer wants to clear out discreetly. But auctions are overwhelmingly dominated by used, off-lease, fleet, and salvage vehicles.
So auctions are really a critical lubricant for the entire automotive ecosystem, especially keeping the used market churning.
Absolutely. They provide that essential liquidity, help dealers manage their inventory balance, and play a huge role in determining used vehicle values.
Wow. Okay, we have covered an incredible amount of ground today. From, literally the raw materials being dug out of the earth, through that complex web of suppliers, the different ways cars are built, the global logistics maze, right up to the dealership, and even the secondary auction market.
It truly is an astonishingly intricate and deeply interconnected global web, isn't it?
It really is. We've touched on the sheer scale, those tens of thousands of parts, the shift from a simple chain to that complex supply web,
Yeah.
the different tiers of suppliers, and how different the supply chains look for EVs versus diesel trucks versus gasoline cars versus hybrids.
And then the whole journey after the factory, the logistics challenges, especially with EV batteries now, the pressures facing dealerships, how they get cars, how they manage inventory, how luxury differs from budget, and yeah, the role of auctions.
Hopefully you, our listener, feel like you've got a much clearer handle on it all now. Maybe less overwhelmed, maybe even found it, well, kind of fascinating. We hope some of those details sparked a few aha moments for you, whether you're prepping for a meeting, just catching up, or were simply curious.
Indeed. And stepping back, thinking about this incredibly complex, globally interconnected system and how vulnerable it can be to disruption, as we've seen, it really makes you wonder, doesn't it? What's the single most critical factor for the industry's resilience going forward? Is it going to be purely technological innovation, better batteries, smarter factories, more efficient logistics? Is it more about achieving greater geopolitical stability so those global flows aren't constantly under threat? Or is it ultimately driven by shifting consumer demand, what kinds of vehicles people actually want to buy and how quickly?
That's a really tough question. Technology, stability, or demand?
It's likely a mix of all three, of course, but thinking about which one might be the ultimate driver, it's definitely something to mull over.
It certainly is. Well, thanks for taking this deep dive with us into the automotive supply chain. If there are other complex topics you'd like us to unpack like this, definitely let us know.
Yeah, we'd love to hear your ideas.
Until our next exploration, take care.